Today's lesson is on reducing radicals. So first we are going to look at the parts of a radical and their terms, what we call them. So we write a radical as n and then the radical sign and b on the inside. So n is what we call our index, and b, which goes on the inside, is what we call our radicand. Then we know that this is our radical sign. Sometimes you'll see this called a root as well. And then overall, we call this a radical. So these parts make up our radical. One thing to note is that if the index is not written, it's automatically a 2. And we've seen that before because when we write, for example, something like this, we know that that's the square root of 4. So we're really saying the second root of 4, which is 2. We just don't always write that 2. It's like how we don't write the understood 1 in front of 1x or as the exponent for our variable x. All right, so there's ways to reduce radicals of numbers. So I'm going to zoom in on that so you guys can see that. So there's a couple of ways to do it. One way to do it is to create a factor tree. Another way to do that is to find the greatest perfect square, or perfect, I'm going to say perfect root, because if we are dealing with the cubed root or the fourth root, then we want to find a perfect cube or a perfect fourth. So find the greatest perfect root that goes into the radicand perfectly. And remember, the radicand is underneath the radical sign. Once you find that, you're going to pull that number out front. And then whatever's left, so the remaining part, is going to stay underneath the radical sign. Sorry, that's an S. All right, and we'll kind of look at what that means in some of the examples. All right, for how to reduce the radicals of variables, what we want to do is divide the exponent by the index. That number gets pulled out front. And then whatever's left over stays inside. And again, we'll see an example of that. By inside, I mean under the radical sign. All right, so let's come look at an example. So we're going to start off doing with the numbers, and I'm going to show you how to do it with a factor tree first. Now, the nice thing about factor trees is that we do not have to start off with the biggest number. It does help. Honestly, I tend to start off with 2 if it is an even number. So this becomes 2 times 125. And luckily, 125 is a perfect cube. It becomes 5 times 5 times 5. So I'm going to cross out the 125 because this is what I want. So 5 is my perfect cube. So that's now going to go on the outside of my radical. I'm going to keep this as a cubed root, and then this stays inside. So once I had my group of 3 because of the index right here, I need 3 5s. So I have a group of 3 5s, so I take 5 outside. And then this 2 goes inside. All right, now what about with our, if we're dealing with variables, how is that going to work? So I can see that my index right there is 3. I want to divide each exponent by the index. So I'm going to do this for x, for y, and for z. And you don't have to break it apart like this. I am mostly doing this to show you the process for each variable. So for x, I've got an exponent of 3 that I'm going to divide by my index. So that's going to give me 1, and I don't have any remainders. So I know that I'm going to pull 1x to the outside. So I'm going to go ahead and write my radical sign like this. I'm going to have 1x on the outside and no x's inside. All right, for y, I'm going to take the exponent, divide it by the index. That's going to give me 1 and 1/3. So I'm going to take this 1 outside, my whole number is going to go outside. And my numerator is going to go inside. So I'm going to bring y. And I don't write y to the first. I could, but that's one of those understood, so we don't do that. All right, for z, I have an exponent of 5. I'm going to divide that by the index of 3. It's going to give me 1 and 2/3. So in this case, this 1 goes to the outside. And then 2, my numerator, stays inside as my exponent. Make that a little long. So I've got 1x, 1y, 1z on the outside, and then I have 1y and 2 z's left on the inside. So this is my final answer. All right, when we've got a combination, you can do it a couple of different ways. Typically, I will break them apart. So I will write this as the 4th root of 48 times the 4th root of z to the 4th. For me, it just helps me to keep them separate rather than trying to do everything at once. So I'm going to start with the numbers so I can do a factor tree. So I'm going to start off with 2, just because I can. Now, our rules above said to start off with the highest perfect square, and you're more than welcome to do that. In this case, I am just going to go ahead and start with 2. And then this is going to become 2 times 24. So now that 48 is gone. 2 is prime, so I'm going to leave that, but 24 I can keep breaking down to 2 times 12. Again, I've got a 2 that's prime. I'm going to keep breaking down 12 to 2 times 6. And then I'm going to break down 6 to 2 times 3. So the important thing to note here is because of my index being 4, I need 4 of the same number in order to pull to the outside. So I have 1, 2, 3, 4 2s. So I'm going to put those together. And that number is going to come to the outside of my radical. And then what I have left over is this 3. That's going to stay inside. So that's the first part. Then I'm going to come over to my variable. I've got z to the 4th. Remember, with variables, we're going to take the exponent 4, divide it by the index, which in this case is also 4. So that's going to give me 1 with no remainders. So what that means is I'm going to be able to take a z to the outside. So this is now times z, and I don't have anything that would be left underneath the radical, so I'm just going to leave it like this. Now when we multiply radicals, we multiply the outside times the outside and the inside times the inside. So I'm going to multiply 2 times z, which is going to give me 2z. And then there's not a radical on the second one, so it's just going to be the 4th root of 3. So this would be my total answer. Right, over here, again, I'm going to break these apart. And if you don't feel like you need to do that, you absolutely don't have to. This time I am going to try to find the biggest perfect number or perfect square that goes into it. So for this one, I know that 16 goes into this. So this is 2 times 16. Cancel that out. Then 16 breaks down to 4 times 4. And then each of those 4s breaks down to 2 times 2. Now, a lot of times I'm happy to just have the 16 because then I can take a 4 to the outside, but that's only when we're dealing with square roots. Since we're dealing with a 5th root here, I need 5 2s. So now I've got 1, 2, 3, 4, 5. So the 5th root of 32 is actually, that's a perfect root. That root becomes 2. All right, now I'm going to simplify my exponents. So I'm going to take the exponent, divide it by the index. 15 divided by 5 gives me 3 with no remainders. So that's going to come to the outside, x to the 3rd. And then we'll just clean that up. So it will be 2x to the 3rd. Like that. All right, we'll flip to the next page. So I briefly hit on this on the front side, but we can use the product rule and the quotient rule to break apart or combine our roots. So I can take, for example, the fourth root of 32. I know that 32 breaks down to 2 times 16. And the reason I would do this is because I know that the fourth root of 16 is 2. Like that's a perfect root. So the goal there is that I'm now going to take this fourth root of 16 and I'm going to simplify that to 2. And then I'm left with this fourth root of 2 for both of them. The same thing can be done with quotients. So if you have a root of a fraction, you can break that apart to the root of the numerator. So that stays the same, and then the root of the denominator. And that helps because, for example, here, the cubed root of 8 is a perfect root. The cubed root of 27 is also a perfect root. And it's sometimes easier to see that when it's broken apart than when you see it as a fraction. So we're going to go through some examples. So I'm going to go ahead and rewrite this. So this is going to be the cubed root of a to the 9th over the cubed root of b to the 6th. Now I'm going to use my rules from the other side. I know that this is a to the exponent, which in this case is 9, divided by my index, which is 3, over b to the exponent, which is 6, divided by the index, which is 3. And now I'm going to simplify those. So 9 divided by 3 is 3, so this becomes a to the 3rd. 6 divided by 3 is 2, so this becomes b to the 2nd. And this is my answer. Right, over here, remember if there's not something written, it's that understood 2, which you can write or you don't have to because we've been writing square roots without the 2 for quite some time. So this is going to be the square root of x cubed over the square root of x to the 4th. So I'm going to go ahead and write this as x to the 3 over 2, which is my understood index. And then the bottom is x to the 4 over 2, which is my understood index. So I'm going to go ahead and simplify those if I can. Now, I cannot simplify this 3/2 just yet, so I'm going to leave that as it is. But 4 over 2 gives me x squared. So the next thing I'm going to do is I'm going to take this 3/2 and I'm going to convert that to a mixed number. So that has 1 and 1/2. So this 1 out front is going to come to the outside of the radical. So I'm going to have x on the outside. I guess I should do. And then the 1 that was my numerator is going to be my inside. So this becomes x square root of x. So I'm going to go ahead and write that. So this equals x square root of x over x squared. Now I've got x divided by x, which I can now simplify. So this is the square root of x over x as my final answer. All right, I'm going to do 2 more. So again, I like to break these apart if I can. So I'm going to start just with this first one for now. So this is the fourth root of 32 times the fourth root of x to the fourth, y to the ninth. And then that is going to be multiplied by the fourth root of 3 times the fourth root of x to the sixth. So I'm going to work on each of these individually. 32 has a perfect fourth root. No, sorry, it doesn't. I lied. 32 can be broken down to 2 times 16. Now 16 has a perfect fourth root. That is 2 times 2 times 2 times 2. So I'm going to put these together on the outside. And this lone 2 is going to be on the inside. So that is that first one simplified. Now we're going to simplify the second part. So x, we're going to do my exponent 4 divided by my index 4, which gives me 1. So that entire x is going to be taken to the outside. Then for y, we've got 9 over my index, which is 4, which simplifies to 2 and 1/4. So this 2 will go on the outside, so y squared. And then 1 will stay on the inside. My next one, the fourth root of 3, does not simplify. So I'm going to leave that as it is. And then for this one, I've got x to the 6th over 4, which is my index. This becomes 1 and 2 over 4. Now it is important here, we need to keep this denominator the same. We do not want to simplify this. So as tempting as it might be to make this 1/2, we don't want to do that because we need the denominator to be the same as our index. So here, this is going to be x, because I've got 1x on the outside, and then the fourth root of x squared. All right, so now I've got all of these parts. They are all fourth roots. So I can multiply all the outsides. So I'm going to make these the outsides. So I've got 2 times xy squared times, there's technically a 1, but I don't have to write that, and then times x. And then I've got my fourth root. And then I'm going to do my inside. I'm going to multiply those together. So 2 times y times 3 times x squared. And then I'm just going to clean this up. So this becomes 2x squared y squared. I've got my fourth root, and this becomes 6x squared y. And that is my final answer. All right, the last one, it looks pretty simple, but we are going to have to do some extra steps here. So I've got the square root of x to the 6th over the square root of 3. So for my numerator, I can take that exponent 6 and divide it by that understood index of 2. And that's going to give me 3. So that alone is going to simplify to x to the 3rd. However, the denominator is not going to simplify. It's going to stay the square root of 3, but we cannot have the square root of 3. We cannot have a root in the denominator. So I'm going to write that. No roots in the denominator. So here's what I'm going to have to do. This is called rationalizing the denominator. So what I need to do is I need to multiply by the square root of 3 over the square root of 3. What that's going to do is that's going to help me get rid of that root on the bottom. So this is going to become x cubed. Oops, let's move it over a little bit. Square root of 3. Ooh, that was a terrible 3. Let's try that again. Divided by, and the square root of 3 times the square root of 3, that's one of those that when you multiply the square root and they're the same, you can go ahead and write it as 3. But just for the sake of showing, the square root of 3 times the square root of 3 becomes the square root of 9. And we know that the square root of 9 is 3. So that's how that becomes 3 right there. So this right here would be my final answer.